Welcome to the deep dive. Today we're digging into a really pivotal paper. Language models are few-shot learners. It tackles something I think a lot of us in ML and data science run into.
Oh, absolutely. It gets right to that core challenge. How do you actually use these big language models for new things without needing, a mountain of labeled data every single time?
Exactly. Like, say you need grammar correction or generating abstracts or even critiquing stories.
Hmm.
Traditionally, that meant huge, specific data sets.
Collecting and labeling all that data, it's a massive effort. And that's one bottleneck.
And there's another issue the paper brings up, which is pretty critical for deployment, I think. These giant models, they can sometimes just learn superficial tricks from the training data. Spurious correlations, they call them.
Right. Which means they might ace a benchmark, look amazing on paper.
But then fail when they see slightly different data out in the real world. They don't generalize well outside their narrow training experience.
Precisely. It makes judging true capability tricky just based on those scores. The paper touches on older ideas too, like meta-learning, which tried to fix this adaptability problem.
Yeah, I remember those approaches. They showed some promise, but didn't quite measure up, did they? Lagged way behind fine-tuning on some key tasks.
That's right. So this leads into a major theme: scale. The sheer size of these transformer models has exploded. We went from, 100 million parameters up to GPT-3's 175 billion.
It's incredible growth, and the paper connects this scaling not just to better performance overall, but specifically to maybe unlocking these more advanced in-context learning skills.
Exactly, in context learning. That's really central here. They explore different ways models might learn on the fly: zero-shot, one-shot, and few-shot learning.
Okay, let's break those down because they're different from fine-tuning, right? No wait updates.
Correct. It's all done with forward passes at test time using the model as is. Zero-shot is just the instruction, like translate English to French.
No examples at all.
None. One-shot adds one example along with the instruction. Translate English to French. Example: C'est hôtel l'outre de mer.
Okay, gives it a pattern to follow. And few-shot.
Few-shot gives maybe 10 to 100 examples. The limit is really the model's context window, how much text it can look at once, which for GPT-3 was 2048 tokens.
So way less data needed than for fine-tuning thousands or millions of examples.
Huge difference. The big advantages are, well, obviously less need for task-specific data, and maybe, just maybe, avoiding that narrow overfitting we talked about.
But the trade-off has always been performance, hasn't it? Few-shot usually wasn't as good as a fully fine-tuned model.
Historically, yes, that's been the catch. The paper also makes a point of separating one-shot, arguing it's kind of how humans often get tasks, like on Mechanical Turk. Just one example to show the format.
That makes sense. And zero-shot. Sounds convenient, but maybe harder.
It can be, yeah. The paper calls it potentially unfairly hard sometimes because instructions can be ambiguous without an example to clarify. Like their example: make a table of world records for the 200 meters dash. What format? Which records?
Right, lots of ways to interpret that.
So they're looking at these settings as different points on a spectrum, trade-offs between how much data you need and how well the model performs.
And the key finding seems to be that with enough scale, few-shot results get surprisingly close to state-of-the-art fine-tuned models.
That's the exciting part. GPT-3, the 175 billion parameter one, showed really promising results in zero and one-shot, and sometimes even matched or beat fine-tuned models in the few-shot setting.
Do they give specific numbers?
Oh, yeah. On CoQA, that's conversational question answering, it got 81.5 F1 zero-shot, 84 one-shot, and 85 few-shot. Pretty impressive climb.
And you mentioned trivia QA.
Right, closed book QA.
Right.
64.3% accuracy zero-shot, 68% one-shot, and 71.2% few-shot. That few-shot score was actually state-of-the-art for closed book QA at the time without any fine-tuning.
Wow, okay. That's significant.
Definitely. And figure 1.3 in the paper gives a kind of high-level visual summary across lots of tasks if people want a quick overview.
Good to know. What about the model itself? You said 175 billion parameters based on GPT-2.
Yeah, same basic transformer architecture, but they incorporated some modifications like alternating dense and locally banded sparse attention, drawing from the sparse transformer work.
And they didn't just build the big one, right? They tested scaling.
Exactly. They trained 8 models in total, going all the way down to 125 million parameters. Let them really study how performance changed with size. Table 2.1 has all the specs.
That systematic approach is important. And the training data, huge amount.
300 billion tokens for all models. Massive compute effort, as you'd expect. Figure 3.1 shows the training curves, supporting this idea that validation loss improves predictably, like a power law, as you scale up the model and compute, assuming you do it efficiently.
It's interesting. Figure 2.2 points out that their 3 billion parameter model used similar compute to Roberta Large, despite being bigger. Efficiency matters.
Absolutely. Now, something they grapple with quite openly is data contamination.
Ah, right. Training on the whole internet means you might accidentally train on your test data.
Exactly. If the model sought the questions or examples from the benchmark during pre-training, the evaluation isn't really fair, is it?
No, it inflates the scores. Did they try to fix that?
They did. They tried to filter out overlaps between their pre-training data, based on Common Crawl, and the dev test sets. But they mentioned a bug meant the filtering wasn't perfect.
And retraining these monsters is not cheap.
Not feasible, basically. So instead, they did a careful analysis, which is in section 4, to see how much impact the remaining overlaps might have had. They created clean versions of benchmarks by removing samples with significant anagram overlap.
How bad was it? Did it skew the results much?
It varied. For most data sets, they concluded the effect was minimal. But some were flagged.
Like which ones?
Well, for reading comprehension like Squad or Drapey, there was overlap, but they manually checked and thought it was mostly background info, not the actual Q&A pairs.
Okay, that's maybe less worrying.
But for PIQA and Winograd, they found more concerning overlaps. PIQA saw about a 3% absolute drop on the clean set, maybe due to some statistical bias learned from the overlap. Winograd saw a 2.6% drop, and they found quite a few schemas in the training data, though in a different format.
So they flagged those results in the paper.
Yep, marked with an asterisk. And for things like Wikitext or the 1 billion word benchmark for language modeling, it was almost total contamination, so they didn't report cleaned results. PinTreeBank was old enough to be okay, though.
Right, okay. So keeping that contamination caveat in mind, how did it perform across different types of tasks? Language modeling.
General trend there.
Yeah.
Bigger model, better performance, pretty consistent.
Makes sense. What about common sense reasoning like hella swag?
Okay, hella swag. GPT-3 in one shot and few shot actually beat a fine-tuned 1.5 billion parameter model.
But not the absolute best score.
No, still below the overall SOTA, which involved multitask fine-tuning. On story close, choosing story endings, it did better than previous zero-shot attempts and got close to fine-tuned levels.
And the closed book QA results were strong, you said.
Very strong. One-shot performance matching open domain fine-tuned SOTA on one dataset, approaching closed book SOTA on others, and performance scaled pretty smoothly with model size there. Figure 3.3 shows that.
Translation was surprising too, given the mostly English data.
Yeah, only about 7% non-English data, but it still showed decent translation ability. Suggests some deeper cross-lingual understanding may be emerging from the scale.
How about those tricky Winograd schemas? Understanding pronouns in context.
It did well on the original Winograd set, despite the contamination issue we mentioned, close to SOTA and human levels. But it struggled more on Winograd, which is designed to be adversarially harder.
Shows there are still limits. What about broad NLU benchmarks like SuperGLUE?
Performance there was really varied. Near SOTA on some tasks like COPA and record, but weaker on others, especially tasks that involved comparing two sentences, like YC or RTE.
So comparing sentences seems like a particular weakness in this few-shot setting.
It appeared so. But overall, the few-shot SuperGLU score did improve with model size and the number of examples K. Interestingly, it outperformed a fine-tuned BERT large with fewer than 8 examples per task on average.
Okay, and NLI, natural language inference, falls into that weaker category too.
Yes, the paper points to NLI tasks, especially sentence pair ones, as an area where few-shot GPT-3 wasn't as strong.
I also tested it on some unusual tasks, right?
Yeah.
Synthetic ones.
Yeah, to probe beyond standard benchmarks, things like arithmetic addition, subtraction, multiplication with different numbers of digits.
How did it do on math? Can it actually calculate?
Performance improved with size and with few-shot examples. It wasn't perfect, especially with more digits, but better than chance. An overlap analysis suggested it wasn't just memorizing answers from the training data.
Interesting. What else?
Word manipulation tasks. Cycling letters in a word, unscrambling anagrams, handling random insertions, reversing words. Again, few-shot helped a lot, and the biggest model was quite capable. Shows it can handle subword patterns.
These aren't typical NLP tasks.
No, they test different kinds of pattern matching and reasoning. SAT analogies were another one. The biggest model got up to 65% accuracy few-shot, showing gains from in-context learning that smaller models didn't really exhibit.
And qualitative stuff.
Yeah.
generating text.
Yes, news article generation was a key one. Give it a headline and a couple of example paragraphs, and it could generate pretty coherent articles in the right style.
Could people tell they were machine generated?
It got harder as the model got bigger. For the 175B model, human evaluators were getting close to chance level, distinguishing its output from human writing even for longer articles. Tables 3.11 and 3.12 show this.
That's quite something. Any other qualitative tests?
They tried teaching it novel words, gave it definitions for made-up words, and asked it to use them in a sentence.
And could it?
In the few-shot setting, yeah, it demonstrated it could often use them appropriately. And correcting grammar given examples of corrections, it showed some ability to fix poor English input.
So, really impressive capabilities, but the paper is also clear about limitations, isn't it?
Definitely. It's not perfect. Text generation can still get repetitive, lose coherence over long stretches, contradict itself, or just go off on tangents.
Not that segues, yeah.
And despite doing okay on some related data sets, it struggles with what they call common sense physics, basic physical reasoning, plus those weaknesses on comparison tasks we mentioned.
So it's powerful, but not magic. It has specific strengths and weaknesses.
That's a good way to put it. The paper also briefly places their work in context, mentioning other scaling efforts, QA research, meta-learning, etc.
Okay, so let's try to summarize the key takeaways for folks working with these models. What are the big points from this deep dive?
Well, first, the emergence of few-shot learning, enabled by scale, as a viable paradigm. GPT-3 showed you could get impressive results on many tasks without fine-tuning. That's huge.
Right. It changes the equation for deploying models on new tasks. Less data needed upfront.
But second takeaway, it's not a silver bullet. Performance varies. There are clear limitations like those comparison tasks or long-form coherence, and the capabilities aren't universal across all problem types.
And third, the practical challenges are real. Data contamination is a tricky issue for evaluating any model trained on web-scale data. We need to be mindful of that.
Absolutely. And tied to that is the whole issue of bias, which they also discuss.
Yes, the broader impact section. We should definitely touch on that. What did they find regarding bias?
Unsurprisingly, training on vast amounts of internet text means the model picks up internet-scale biases. They looked at gender, race, and religion.
What kind of gender biases?
They found associations between certain occupations and male pronouns. Prompts using words like competent tended to amplify this male bias. Also, analysis showed female terms co-occurring more often with appearance-related words.
Okay, and race.
They analyzed sentiment associated with racial terms. Consistently higher positive sentiment linked to Asian and lower sentiment linked to Black across different model sizes. Using CentiWordNet for measurement, Figure 6.1 shows this.
And religion.
Similar co-occurrence analysis. They found terms like violent and terrorism co-occurring more frequently with Islam compared to other religious terms. Table 6.2 has examples.
So these biases are baked in from the data. That's a critical point for anyone using these models.
Hugely important. The paper also discusses potential harms, misuse for misinformation, spam, phishing, academic fraud, social engineering. The better the text quality, the higher the risk of misuse.
Did they look at who might misuse it? Threat actors.
They did some analysis. At the time, lower-skilled actors weren't heavily using it, but improved reliability could change that. Advanced groups, APTs, didn't seem to see a huge advantage over existing methods yet, partly due to lack of fine-grained control. But the potential is clearly there.
Alongside beneficial uses like coding help, writing assistance, better search.
Right, it's a double-edged sword, as with many powerful technologies.
So wrapping up the takeaways. Few-shot learning is powerful, but not perfect. Contamination is a concern, bias is inherent, and needs careful mitigation.
And in context, learning offers this different way to adapt models quickly, a new trade-off versus fine-tuning. Lots of open questions remain: improving few-shot, tackling bias, better evaluation, ethics.
It really opens up a lot of avenues for future work.
Definitely. And it leads to that final thought. Given how fast things are moving, how might these capabilities and limitations fundamentally change how we interact with technology and information? What shifts should we anticipate?
That's a big question to ponder, a lot to think about for anyone in this space. Thanks for joining us for this deep dive.